Okay, I have prepared the signal block diagram of this final last project. Here's a list. Now with this button you can open this block parameter list. Block 5 is a P controller with 15.8 gain. Block 1 is PDT1 with 10 milliseconds. Block 2 110 milliseconds. Block 3 50 milliseconds and the gain 1.6. The integrator has an 0.1 gain factor. Then block 6 was the sensor with 1.25. So this is the system, and we can close this box and start the calculation of the reference step response. Later, of course, you can do the next steps. Note that this is 71. You have two identical numbers. This comes because I have changed this out of another plan. If I click on this button, then of course I get a new so I get a new the old codes of the last project. I get a new numbering. You see here, node 71 is here the number of Z1, 73 the number of Z2, 72 the number of the reference input. So if you calculate step responses, we have to note these numbers, because in my box here I can select these numbers. And 72 was now the reference input. I want to see the reference step response. Output block number 4 is a controlled value. Time range 5 seconds. I'm not sure if this is okay. I want to have a unit step function, and here you see the unit step response of my P controller with a final value 0.8, which is caused by the sensor gain 1.25. If I switch to output block 6, you will at once see this goes to 1, so the control error here is really 0, because the sensor output is controlled to an output of 1. But this caused a sensor input of 0.8. So this should be clear. Okay, that was a P controller. Now I store this curve and go into the I controller. So I mark the P block and go to the PI block and simulate now the our controller PI. The time constant is already not calculated yet, so I have to wait for these numbers until I have looked on my reference list. The Tn value is not known, but with the omega d value, with this equation, I can very quickly calculate the Tn value. So let's do this job. Omega n is 1 over Tn is with omega n is 0.577 times omega d, and Tn is then of course the inverse. It's 0.577 times omega d. With our results 1.6, we have 1 divided by 0.577 times 1.6 per second. You see that is really a time. In my calculator I get the result 1.08 seconds. 1.08 seconds. I have to check. This seems to be strange, but I have to check. Yeah, indeed, I have made an error. This 0.566 value belongs to a phase margin of 30 degrees. We are at 60 degrees, and there our omega n over omega d value is 0.268. Sorry for this. So we have to correct this 0.268, 0.268, 0.268. Sorry for this mistake that happens, and I calculate now the new value is 2.33 seconds. Yeah, that is that I have seen very often in my resulting papers. So this is a TN, and the KC comes again with the calculation. No, I have done this. Sorry, KC is 7.6, 2.33 for the time constant. So we can now type in the values. 7.6, and this gives 2.33 seconds. We say OK, and can now calculate the PI response. Is output block 4. Okay, I have to check what happens here. Okay, yes, I have seen this. Sorry for this. I have to explain it. I have changed this block and then redo the calculation of the step response anytime where I click on this button and I've changed the structure of the system, and a change of a block is a change of the structure of the system. Then the system makes a new counting of the input numbers, and the input numbers have changed. Sorry, the 73 input was now my reference input, and I have calculated this with 72. That was a disturbance at the output. Sorry for this mistake. I have to check here with 73 and recalculate it, and now I see the reference step response of my system controlled with a PI controller, and you see if we wait long enough, then this ends up in the final value 0.8. You see much slower. The overshoot is much bigger than P. So this is worse. The reference behavior is worse compared with P, but the disturbance behavior is better. I will calculate the disturbance responses after I have designed the both other classical controllers PDT1 and PIDT1. Then we make in this simulation also the calculation of the disturbance step responses. Yeah, I think I should add here the line from the value 0.268, and I should correct my wrong values. Now let's finalize this design with the PDT1 and the PIDT1 controller. This should be number 4, PDT1. Maybe this number is a little bit different to the old student script. PDT1 with phase margin 60 degree and with step depths 10, standard values. For this we have a selection to make. Selection of TD should be made, and this can be done with pole compensation. Pole compensation for PI is forbidden, but pole compensation for the PD is possible. So this could be then the largest one, largest process time constant. That comes from the fact that the PD replaced not of course the PD replaced a 0 with a pole, but then the PI replaced the 0 with an integrator, the PD with a new PT1. So this is easily done. Selection of TD is 0.11, the largest process time constant. Pole compensation. is allowed in the PDT1 case. No problem. And we get the following result. So what we have to do is add the controller phase VC, which can be calculated. The equation we have used in the section 5.2, arctangent omega TD minus arctangent omega TD divided by step depth. So we add this phase, which is positive, and the result can be found in the workbook page 44. This is a top border plot. Let's open this page. Here you see the unchanged blue magnitude curve of the process, the unchanged red phase curve of the process, and here you see the green curve that is new. That is, if we add to the process the positive phase values for each point of the PDT1 block. And the cross point now with 60-degree phase margin is at minus 120 with a green curve, gives a value 7.6. So we have here the result. Omega d is 7.6 per second, and the magnitude value here at the curve is process magnitude at omega 7.6. How large is this? Oh yeah, you see this is 0, this is 100. Oh yeah, this is negative 34 dB, negative 34 dB. So result, omega d is 7.6, is cross point of new phase, green curve, open loop is controller phase plus process phase at minus 120. This comes from the phase margin value 60. Okay, so we have, this is of course 1 per second, a value of 7.6. Note, compared with the P controller, there we have an omega d of 3.2. So we are have more than double speed than P. But of course, the control error in the disturbance KC1. We need the KC value. KC with open loop magnitude at omega d is 1. And with this equation you get a KC is, don't want to do this in details. In my workbook you see the details. With this negative 34 dB value you get a KC of 40. With FC at omega d 7.6, magnitude is negative 34 dB. Okay, so we can simulate this controller. Simulation needs the KC value 40 and the TD value 0.11 and the step depth value 10. So we open now the signal block diagram. The PDT1 can be realized with my PIDT1 block, where we set the time constant to a very large value. The gain is 40, time constant of the numerator was 8.11, and the step depth was 10. We say OK, look for the numbers of the inputs is not changed. Here that is 73, so 73 is OK. Output is still 4, is also OK. So we calculate, we store this red curve and make a recalculation, and you see the green curve is a PDT1 reference step response of my system, of my closed loop system, is much faster. With these lines, maybe it could be more easily to check the speed. This is smaller than 0.4. This is 0.8. It's a factor of 3. Nothing more we can say. That factor of 2. That we have double speed with a PDT1 controller. So you see, much better. Same final value, 0 control error. If you can afford this high actuator peaks, or if the cut of a limiter of the actuator has no other negative effect, then take a PDT1. Yeah, in the table on page 45 in the workbook, we can compare now our 3 designs. We have a P, a PI with symmetrical optimum, and a PDT1. You see the PI pole compensation can be excluded because instability. You see here the speed indicator. This is more than double speed of this, but note that the Kc times step depth value, if you compare the actuator peak value, then we have here is 16.6 times 1, and here a 40 times 10 is 400. So the peak value of the actuator is 400 to 16 is more than 20 times larger for double speed. So you have to check if your user is willing to pay this price. Yeah, let's make a note for this. Peak of actuator value in reference case. PDT1. We have here a Kc step depth is 16.6, and here we have 400. That means, and speed, speed is, the speed indicator is the ratio. Speed indicator P is the omega d value. What was this? Omega d value is 3.2. 3.2. Speed indicator in my PDT1 case, where is this omega d? 7.6. 7.6. So the ratios are, here you can see 2.4 times faster PD gives a 24 times larger impulse. So this is a factor of 10 of inefficiency. If you want to have double speed with double amplitude, that would be good, but you have here double 2.4 speed with 24 times larger amplitudes. That is unaffordable, I think. This comes for the because of the large step depth values of 10. Okay, then last point, finalize this with the PIDT1, phase margin 60 degree, step depth 10. My example, my selections, TN the PI, not with pole compensation, not allowed, unstable, same situation. So we have only here the chance to go with symmetrical optimum, and TV with pole compensation. Now, the PI is not allowed with pole compensation. The TV, of course, can be done with pole compensation. So we have here a TV, which is 0.11 than before. Here we have a controller phase at omega d, selectable out of the symmetrical optimum table. Again, it's minus 15 degrees centigrade. So what we have to do is steps: add the phi PDT1 phase to controller, to process, sorry, to process. This same curve as the point before with the PDT1, so we can go into the same diagram. Then look for the cross point at minus 105 degree. Okay, let's do this job in the Bode plot diagram, PIDT1. Yeah, the same curve, unchanged, but the cross point now is shifted a little bit higher. Now the PDT1 is a cross point here, the PIDT1 has a cross point here, so you see the value of the crossover frequency goes down to a value of 3.7 or so. What is the result here? Omega d, next page, is 3.8. 3.8. Omega d is 3.8 per second. The process magnitude at omega d can be read out of the curve here. You see here, this is this point, and this points to a value calculated with my cursor function to negative 26 dB. Negative 26 dB, and with the same methods this leads to a Kc factor. So the next steps are just unchanged. Kc factor of 18.7. You see here the Nyquist equation, or the magnitude, the open loop is 1, is controller magnitude, process magnitude here is the 26 dB value, and this is the equation to calculate the magnitude of the PIDT1 controller. Omega d is known, is given to 3.76. Tn is at this time unknown. Yeah, we have, of course, looking into the symmetrical optimum design, how to calculate the Tn value, and T value is 0.11, step depth is 10. And with these values you can calculate 18.7, but before you can calculate this, the Tn value has to be calculated in the same manner as before. Here Tn is 1 divided by 0.268, 1 divided by 0.268, the factor relating out of the table relating to the phase margin of 60 degree. No, this differs if we change this and multiplied with the Tn divided by the omega d value. Divided by omega d. Okay, this gives a number. Omega d is 3.8. ohms, 3.8. This gives a time constant of 0.98 seconds, round about 1 second. Okay, look in the simulation. In my paper workbook, I have calculated 0.99. Here in the table, here you can see now what we have as a resulting value: 3.8, 18.7, 1 second, pole compensation for the TV value, step depth 10, all things okay, and pole compensation is not allowed, unstable. So we have to finalize this with simulation. We go now with these numbers into our simulation. Note K is 18.7, 1 second. So we have now a signal block diagram. The values here are proportional gain 18.7, PI time constant 0.99. The rest is unchanged. Say OK. Calculate the green curve is stored now, and now I calculate the PIDT1 reference step response. You see here nearly a 14% overshoot. Final value for all controllers is the same, unchanged. What I have told you, that this comes from the sensor, and you see black curve and blue curve has the same maximum value, but the black curve needs more time to settle down to the final value in a 10% tolerance range. Of course, then the P controller is faster than the PIDT1 controller. Note this. I think we should calculate now the disturbance step responses of all curves. So I think I store this result as a chart in 3 PDT1 plus I ref RSR, reference step responses. I clean the curve and I show you how to calculate now very easily the disturbance responses. The disturbance here is 71, so just I go down to 71, then I get disturbance of all controllers. I want to do the same colors with the same controller type, so I don't want to record this. I just can show you this is the disturbance response of the PIDT1 controller, just realized, but of course I want to have 4 curves with all 4 controllers we have designed. So I stop recording and you get the final result at once for you. So you see now the disturbance step response of the P controller. Note this 0.03 is calculated in my paper at this position, where I have this position P controller here. This factor is the output value if we have a disturbance at Z1, and then the X goes to 0.03. You can see this here. Then the PD has much smaller value because the K is much larger. The K is 40. So this controller gain, this larger controller gain makes a smaller control error in the disturbance behavior. The PI pulls down the output to 0 as desired. I want to have it. And the PIDT1, of course, here is much faster than PI. So here you can see for the disturbance behavior, the PIDT1 is just the best so far.